Dear friends, hello. Dear friends, hello. Grigor is here today with you. Today we have, from my point of view, one of the most important topics for your exams, especially your physiology exam. Some of those questions might be also included in your biochemistry exam. But also, I would say this will be useful for your biophysics exam if you are a first-year student. So this is basically useful for nearly everyone who is in the beginning years. So let's start with the beginning of the membrane potential, because this is our topic for today. Then we will talk about the different kinds of membrane potential. What is the membrane potential itself? We need to give the definition first. This is the electric potential difference between the interior and exterior of the cell. So this is basically the potential difference or the charge difference between the inside of the cell, intracellular space, and outside of the cell, extracellular space. Well, the membrane potential cannot be at a zero for a living cell. It cannot be at a zero. It will be zero if you have a dead cell. So we now need to understand how these resting membrane potentials are, how these membrane potentials in general are reached. Well, clearly, to have the difference of the electrical potential means difference of charge. You need to have different amounts of charged molecules inside of the cell and outside of the cell, because this is how you reach the difference. Well, to talk about the potentials, we need to, first of all, define what kind of potentials we do have. We have the resting membrane potential, which is basically the membrane potential at rest. So this is applying for the I would say, excitable tissues, like, for example, not muscles, not nerves, like, for example, just, I don't know, skin cells, or I don't know, let's say, just normal like epithelial linings, I don't know, some other, virtually all your cells in your body, I don't know, connective tissue cells and all of those, but not excitable tissues. Yeah. So with the potentials, we also have action potentials. This is basically the so-called excitable tissue potential, which is obviously the nerves and muscles. Please remember one more important thing, that the resting membrane potential is not present in three kinds of cells, because resting membrane potential is somewhat a steady value. Yes, it can change, but it is somewhat a steady value for some period of time. You know, it is constantly changing, but again, this is like at a stable value. It's not like, kind of like waving around. Yes, so these three types of cells that do not have resting membrane potential, please remember, this is important for your physiology exam, include the pacemaker cells. What are those? Those are Cajal cells in your GI tract, which is the part of the enteric nervous system. Also important, the pacemaker cells of your heart. Yeah, so sinoatrial node, atrioventricular node cells, all of those nodal cells do not have resting membrane potential. Their potential constantly goes up, reaches depolarization level, goes down, goes up, reaches depolarization, goes down. So it is constantly, there is no steady state called resting membrane potential. Also, the reticular formation cells. This might be somewhat surprising for you, but yes, this is mentioned by the lecturers in our physiology department. So please remember this as well. Okay, and graded potentials. Graded potentials, in other words, are called postsynaptic potentials. Basically, graded potentials is how much the potential changes when a bunch of neurotransmitter is released on your postsynaptic membrane, and it deviates the membrane potential into a small value. This is called the postsynaptic potential or graded potential. So this is basically, again, this is a membrane potential change with the release of one, let's say, unit of neurotransmitter on the postsynaptic membrane. But what are we interested more right now is the resting membrane potential. The basis of the membrane potential are ions. So please remember the concentrations of the ions. This is how it is given to in Guyton, but we will remember it in a more easier way. We will remember it by the rule of 4. So you see, nearly in every number in these 1, 2, 3, 4, 5 in the beginning. So sodium, potassium, calcium, magnesium, not that much, but chloride and bicarbonate concentrations are one of the most important ones that you should know for sure. So please know that sodium outside is 140. So already one of the 4s in here, 140. Inside, it's usually 14. So we just want to have number 4 in there. 14 is normal concentration of sodium inside. So we will say, so sodium outside 140 and inside 14. Potassium in the outside is 4. Inside 140. Calcium outside 2.2 to 2.4. Usually they want to hear 2.2, but 2.4 is also fine. So 2.4, and inside it's nearly 0. Chloride 104 outside, and bicarbonate 24 outside. So you see, in all of those numbers, we have the numbers 4. Okay, so as I said, the resting membrane potential is not a steady value for different tissues. And it is not like, one standardized value for the tissues. So your skeletal muscles, neurons, smooth muscle cells, and others, they have different values of resting membrane potential. Now, how do we count this resting membrane potential? We need to count something what's called electrochemical potential. So electrochemical potential is basically where the ion wants to go according to the concentration difference and the charge difference. In other words, inside of the cell, as we saw in these values, inside of the cell is negatively charged because this value is how negative is because is the difference between inside and outside of the cell. So your inside of the cell is 90 millivolts less than outside of the cell. So inside of the cell is more negatively charged. That's why positively charged ions, like for example, sodium, would tend to go inside the cell according to the electrical gradient, because sodium is positively charged and inside the cell it's negatively charged. So they tend to attract. But also what drives sodium inside is the concentration difference. So sodium, according to the concentration difference, would like to establish the equilibrium of the concentration. If the membrane was fully permeable to sodium, sodium would have flown in and established the concentration equilibrium. But it cannot do that. We will talk in a little bit later why. So two forces that drive the ion in or out. First of all is the electrical force, second of all concentration gradient. But let's look at the potassium, for example. Potassium is positively charged. So it will tend to stay inside the cell according to its electrical charge, because again, inside the cell is negatively charged, outside is positively charged in comparison to the intracellular space. But look at here. The concentration difference in here matters. It's nearly like what? 35 times more inside the cell than outside the cell. So this huge, gigantic concentration difference plays a huge role in calcium, in potassium, kind of like net force. So electrochemical potential is the summary of is the sum of electrical and chemical potential of the ion to go in or out the cell. When the cell reaches something what's called electrochemical equilibrium, this means that electrical and chemical potential are now in harmony, equilibrating. So there is no net outflow or inflow, net, very important word, net inflow or outflow of the ion. Ion is not going anywhere, net. Well, this cannot be shortly explained because usually in the physiology seminars we used to teach this for much longer time. But since we are a little bit limited in time today, I need to stop with this concept. But if you would like to see the continuation, please let us know. So we know that all of the, but now you can ask me, how are those concentration differences established? Why, for example, sodium cannot flow in if it has both like concentration gradient and electrical gradient, which drives the sodium in? I would answer you, semi-permeable membrane. The membrane is not permeable for everything. You know, membrane is permeable for small and non-polar molecules. For example, it is even not permeable for water. It is permeable for, like, for example, gases like oxygen, I don't know, NO, NO2, CO2, and all of those. But it is not permeable even for water, because water is small, but it is a polar molecule. So please know, and obviously your ions are polar as well, they're charged. So they will not go through your membrane easily. Okay, now let's talk about the how the ion can go through the cell. It needs to use a channel. And these channels include leaky channels, voltage gated channels, ligand gated channels, and mechanically gated channels. Voltage gated channels obviously open if there is a change in the voltage, if there is a change in the potential of the cell. So if the voltage changes, the ion flows, the channel opens. If ligand is there and ligand opens the channel, it is called ligand gated channel. So ligand, some sort of a signaling molecule, like for example a neurotransmitter, came and told the channel to open and for the ion to flow in. This is called ligand gated channel. Leaky channels are always open. Most important leaky channel that you need to know is potassium leaky channel. Please remember this. Okay, now when we talked about the channel types, we can talk a little bit about the pacemaker potentials. So the pacemaker potentials, again, this is, for example, the example of the pacemaker cell in your heart. This is the cells of the sinoatrial node. And as you see, they do not have the steady state. They do not have the resting membrane potential. I will skip all of these because this is not very important for us right now, as we need to go into the action potential. So now let's talk about the action potential. Action potential is only applying to your excitable tissues. As I said, those are the neurons and cardiac cells, muscle cells, and like skeletal muscle cells, smooth muscle cells, and so on. Action potential is reached because you excite your tissue. So imagine this. You are trying to push a sofa or a bed, which is very heavy. You need to apply some sort of force, the beginning force, in order for that bed to move until you reach that amount of force. And when you reach that amount of force, this is called the threshold potential. So you reach some point of the force where your bed starts to move. And this is the same with the action potential. Action potential is nearly the same. So action potential is when you reach the threshold potential, and so-called voltage gated. So they open when the voltage changes, when the membrane potential value changes. Sodium channels usually. Let me go into this diagram. You see, in here you have the example of a non-threshold potential, so-called gated potential, so-called graded potential, I'm sorry. And you see, the graded potentials can be summed to reach the threshold. I hope this makes sense. When you reach this threshold potential, most of your voltage-gated sodium channels, all of them, open and momentarily close. Whenever the membrane potential fires, usually this gap to the threshold potential, difference between the resting membrane potential and threshold potential, usually it is somewhere around 15 to 20 millivolts. So if your resting membrane potential is minus 70, the threshold will be something like minus 55, 50. So let's say that you have the graded potential or this threshold potential reaching the threshold level of 50 minus 50 millivolts, you fire the action potential. As soon as the potential reaches about a 0 millivolts, these channels shut down. They are fast, they shut down. And then you have this spike. When you also reach the threshold level, you open at the same time voltage gated potassium channels. But the interesting thing is they are not as fast as sodium channels. So when your sodium channels open fully and give this spike, the potassium channels still are opening. And at this state, the maximum amount of potassium channel opens, and then the membrane potential drops, even may drop lower than resting membrane potential. This is called hyperpolarization. And after hyperpolarization, it again reaches the resting membrane potential. Now, this is a big concept to go through, and this is not so simple. Again, in 15 minutes, it is absolutely impossible to go through all of these mechanisms because there is a lot of other, I would say, other important things that we need to go through, but we will simply stretch the lecture up to like an hour or an hour and a half. I hope you do not want to see this. So if you would like me to clarify, you can simply text me. You can, I don't know, give me a call even or something like that. You can ask our physio students who are in our physio lectures, and we will clarify everything what is needed for you. You can also write in the comments your questions, and we would love to answer everyone. We would love to give you as much information as we know. Again, this is a very short overview of the action potential and resting membrane potential. We did not even talk about much the grading membrane potentials, which are absolutely essential, as you see in this picture, actually. So I hope that it was more or less clear, and it was like a good summary, or maybe for some of you, a good beginning of the membrane potential concept. And I hope that this was more or less useful for you. And I see you next time, I guess. So have a nice day and good luck with your exams.